Hamilton. This video was part of a submission that I made for my master's research project at university. The project looked at using machine learning and more specifically artificial neural networks to make a tool for aerodynamic analysis. The video itself is quite formal because, as I said, it was part of a university submission, but I really wanted to upload it here just to showcase an amazing real-world application of data science and machine learning, and to show some of the work that I've done in the field. So, let's jump in.
Artificial intelligence and machine learning have become increasingly popular areas of technological development over the past decade. Machine learning is the study of algorithms and statistical models that give computers the ability to learn from data and make predictions or decisions. This can allow computers to perform tasks without explicit instructions by the detection of patterns and inference. Countless industries have started realizing the benefits of machine learning, including the healthcare, financial services, and aeronautical industries. Artificial neural networks are a specific machine learning technique that consists of many connected artificial neurons, typically arranged into layers. Networks typically have an input layer, a set of hidden layers, and an output layer. The exact way in which a neural network operates would make up an entire video presentation in itself, but in its simplest form, a set of values is given to the input layer, with one value being assigned to each neuron. The values undergo a series of mathematical operations across each of the layers, producing a value in the output layer. This output is the network's prediction based on the given inputs. Specific use cases for neural networks include Google DeepMind's AlphaGo, a neural network capable of beating the 18-time world champion in a game of Go, self-flying drones, such as this one made by Skydio, and Andre Esteva's mobile phone application capable of detecting skin cancer to the same level of accuracy as a professionally trained dermatologist. So, with machine learning being implemented in countless fields and industries, the aim of this project was to investigate if machine learning could also have beneficial contributions in the field of computational fluid dynamics. Specifically, the project investigates the use of artificial neural networks for the modeling of aerodynamic flows. So, why might this be an interesting subject? Well, computational fluid dynamics is generally a computationally expensive, time-consuming process. Machine learning shows a real opportunity to provide vast time savings over conventional methods, opening up the possibility of real-time aerodynamic design. The majority of existing uses of machine learning in CFD involve the tuning of existing CFD turbulence models, while some combine CFD and machine learning to flow optimization problems. The area of most interest to this project is the use of CFD results as training data for a neural network designed to predict flow characteristics and flow fields. Zhang used neural networks to predict the lift coefficient for a given aerofoil shape and flow conditions. However, the results presented were minimal, and it was therefore difficult for any real conclusions to be drawn. It is hard to prove how the model was performing and where its weaknesses and strengths lie. This provided an opportunity in this project to do a more detailed analysis on a similar neural network. Furthermore, the aerofoils Zhang used to test his model were all part of the training dataset. A more beneficial assessment would be to see if the model could predict the force coefficients for aerofoils which are different to those on which it was trained. Batnagar attempted to predict velocity and pressure fields for unseen aerofoils in different flow conditions. The neural network was shown to accurately predict new flow fields orders of magnitude faster than a round silver. However, only 252 datasets were used. This set of 252 data points only included 3 different aerofoils. Furthermore, the aerofoil used for validation was very similar to those used for training. So it's decided that the current work should focus on using a greater variety of training aerofoils and testing the network on aerofoils that are significantly different to those on which it was trained. Both Zhang and Batnagar used convolutional neural networks in order to pick out salient features of the airfoil geometry. The neural network needs to be able to recognize and process images, and convolutional neural networks have been shown to be very good at image recognition tasks. Convolutional neural networks are, however, more complex than a simple multi-layer perceptron, so it was decided that the current project should look at both architectures to evaluate if the added complexity of a convolutional neural network provides any significant benefits. Based on these accomplishments and pitfalls of the previous work, a set of objectives was defined to ensure the project would provide an original contribution to the field and answer some of the questions raised by previous work. The full set of objectives are shown here, But the main takeaway is that the project's aim was to build and test a variety of neural networks capable of predicting aerodynamic force coefficients when given an aerofoil's shape and flow conditions, and that the assessment of the neural networks should focus on what architecture gives the best results and what the benefits of the neural network is over conventional CFD methods. The first place to start in the creation of the neural network was with the gathering of training data. To understand what data needed to be gathered, it's easiest to look at an example of how the neural network may look. As can be seen, there are three inputs to the proposed neural network. The first is the airfoil geometry, and the other two are simply the free stream Mach number and the angle of attack. The gathering of this input data is fairly simple. The Mach number and angle of attack are simply numbers which we can specify. The geometry data is slightly more complicated. The airfoil geometry is taken from a website called Airfoil Tools in a coordinate-based format. This is then used to create an image of the airfoil from which the pixel values can be obtained. The output data is where the majority of the work lies in terms of data collection. In order to train the neural network, actual values for lift and drag coefficient are required. The collection of these values was carried out using CFD. Contour plot images for the velocity and pressure are also collected, as further work may include the adaptation of the neural network for flow field predictions. It was decided that training data should be collected for 8 aerofoils at 41 angles of attack and 39 Mach numbers. This means there were 12,792 CFD simulations required. StarCCM has an automation capability provided through its Design Manager program. The program allows for a single simulation to be set up with flow characteristics such as Mach number and angle of attack being parameterized. Design Manager is then given a range over which to vary these parameters at given increments. The program then runs a simulation for each unique case. Design Manager allows for multiple cores to be dedicated to each simulation or several simulations to be run on individual cores simultaneously. For the best use of parallel efficiency, in this case, 12 simulations at a time will run on one core each. In total, the 12,792 simulations took around 80 hours, equating to 270 CPU seconds for each simulation. For the purpose of demonstrating the accuracy of the training data, the CFD results were evaluated in some detail. The velocity, pressure, and Mach contour plots are shown for the RE2822 aerofoil at Mach 0.725 and an angle of attack of 2.92 degrees. The contour plots show that the simulation captures the flow features well. Firstly, a leading edge stagnation point is seen where the velocity tends towards zero, and the pressure coefficient is at its maximum. All of the contour plots also show the shock wave clearly, as well as trailing edge separation. Closer inspection also shows that the boundary layer is being captured well. The surface pressure distribution predicted by the simulation is also shown in comparison to experimental results. It's seen that the simulation is very accurate, showing good agreement with the experimental results. Results for the range of airfoils and flow conditions were also assessed and showed similar levels of accuracy. It should be noted that data from the Design Manager was automatically saved into the Windows file system, which is not ideal for importing during training of the neural network. A faster and more efficient way is to store and retrieve data in a database. For this, SQLite was used. So, once the data has been collected and stored, it's time to move on to the creation and training of the neural network itself. The neural networks were implemented using Python. Python was chosen for its dedicated open-source machine learning library TensorFlow, which is recognized for its easy implementation and reliability in neural network creation. TensorFlow is also capable of utilizing graphical processing units. Keras is a high-level application programming interface used on top of TensorFlow. It enables each layer of a neural network to be defined in a few lines of code, as will be demonstrated in due course. Through preliminary trialing, two main neural network architectures were chosen, a multi-layer perceptron and a convolutional neural network. The multi-layer perceptron is named AeroNet1. It consists of an input layer, 4 hidden layers of decreasing size, and an output layer with 1 neuron for each force coefficient. Aeronet1 has a total of around 1.2 million trainable parameters. The second neural network, Aeronet2, consists of 2 separate input layers, one for the pixels of the geometry image and one for the 2 flow conditions. The first input layer goes into a convolutional and pooling hidden layers section. The flow conditions are then input after the convolutional layers. Fully connected hidden layers then decrease in size until the 2 output neurons are reached. Aeronet2 has a total of around 430,000 trainable parameters, which is considerably less than Aeronet1, but added complexity lies in the convolutional and pooling layers. As well as the architecture of the neural networks, there are many hyperparameters that need to be chosen and tuned. For brevity, the function of each hyperparameter and the reason for choosing it are omitted from this presentation, but final chosen hyperparameters for each model are summarized in this table. I'm now going to show you how the neural network I've been describing is actually implemented. So the code you can see was the code used to implement Aeronet 1, the basic multi-layer perceptron. The first section of the code is the creation of the model architecture. Using Keras allows you to easily specify each layer in a few lines of code. For example, this is the second hidden layer, which you can see has 522 neurons. The kernel initializer, bias initializer, and activation functions can all be specified as spoken about in the previous slide. Once you've defined the architecture of the model, the optimizer and loss functions are defined. For example, here we see the Adam optimizer and root mean squared error loss function being defined. The model can then be compiled and is ready for training. Once the model is fully defined, the data is imported from the SQLite database. The data then requires certain manipulation before it can be passed to the network. For example, the input values must be normalized between 0 and 1, as this improves training performance. Finally, the model can be trained. This section of code is where the batch size, number of epochs, and split between training and validation accuracy can be dictated. So, if I click Run, I can give you a rough sense of the time it takes to train the model. In total, Aeronet 1 took 27 seconds to train over the 100 epochs, and Aeronet 2 took 39 seconds. Finally, the trained model is saved so that it can be used to make predictions on new data points, which is done in a separate program. These graphs show the training and validation accuracy for each of the models. Both models were trained across 100 epochs with batch sizes of 256. The training of Aeronet 1 took a total of 27.34 seconds, with a final training accuracy of around 98%. Aeronet 2 training took slightly longer at 38 seconds, but also has a slightly higher training accuracy of nearly 99%. So, once the models have been trained, you can simply feed new airfoil geometries in with flow conditions, and the models can make predictions for the force coefficients. On average, the networks take less than 10 milliseconds to make a single prediction. When compared to the 270 seconds to run a single one of the CFD simulations, the potential time savings are clear to see. I gathered more CFD data on some airfoils that the neural network had not been trained. I then used the models to make predictions for the new airfoils and can compare the results. In total, 420 predictions were made for each airfoil. The accuracy of the models when making predictions on each airfoil and overall is shown. It is seen that Aeronet 2 is significantly more accurate than Aeronet 1 for predictions made on the NACA M27 airfoil. It's also seen that the two models have similar accuracies for the other two airfoils, with Aeronet 1 accuracy being marginally higher. This means that overall Aeronet 2 has a marginally higher accuracy when making predictions for these unseen airfoils. Generally, this test accuracy is about 15% lower than the training and validation accuracies. Overall accuracies can be misleading. To get a true picture of how the models are working, some relationships must be investigated. These graphs show the lift curves predicted by the models and the CFD for the three airfoils of varying Mach numbers. The graphs show that Aeronet 1 does not appear to fit the relationship shown in CFD results very well for any of the airfoils. Aeronet 2, on the other hand, appears to predict the trend well in certain cases, such as for the NACA M27 airfoil at Mach 0.9 and the SC20518 airfoil at Mach 0.1. Generally, Aeronet 2 appears to be consistently more accurate for all of the airfoils, but both models struggle with the Mach 0.7 predictions. This is likely to be because in the transonic region, the onset of shock waves and separation can produce unsteady flows. Aeronet 2 slightly underpredicts the lift coefficients on the SC20518 at all angles of attack and Mach numbers. This is interesting, as that airfoil was specifically designed as a high lift producing airfoil. The model was not trained on any airfoils of this type. The training of Aeronet 2 on a greater variety of airfoils is something that should be considered for further work. Now the drag curves predicted by the models and the CFD for the three airfoils at varying Mach numbers are shown. It's seen that Aeronet 1 generally just predicts a slightly curved horizontal line for all Mach numbers and airfoils. It fails to predict the trend of the drag curves in almost all cases. Interestingly though, this may be the reason for its high overall accuracy value, as it's seen that even the prediction of a horizontal line is highly accurate at some points. Aeronet 2 shows very good agreement with the CFD results when it comes to almost all of the drag curves presented. It's obvious here that the convolutional neural network architecture is outperforming the standard multi-layer perceptron. The comparison of results at varying Mach numbers for different angles of attack can give another picture of model performance and helps to get an idea of the performance across the whole of the design space. Again, Aeronet 2 significantly outperforms Aeronet 1 in the vast majority of cases. However, it appears that even Aeronet 2 may slightly underfit the curve in the drag divergence region, where it does not quite predict the sharpness at which the drag coefficient increases. This slight underfitting could be improved by training the model on more data points in the Mach number sweep. All in all, the results have shown that a neural network can be used to predict aerodynamic force coefficients. Aeronet 2, the convolutional neural network, was shown to be the superior network architecture for this task, with an overall training accuracy of 98.8% and a test accuracy on unseen aerofoils of 84.7%. With further work, such as training on more aerofoils and the expansion into 2D and 3D flow field predictions, this could pave the way for real-time aerofoil design and even real-time aerodynamic design in general.